Morning, everybody. Any questions before we start? That's not what I want. Okay, so today we're going to talk about visualization. So some of you might remember this slide. Actually, some of you might not remember this slide. We had this slide, we showed this slide last week. Ways to support conclusions with data. And we mentioned statistics, visualization, and inferential statistics. So today we're talking about this visualization. And visualization is essentially using computer graphics to generate images of data. Right? Data is really only good if you can see it. It helps to be able to see it, right? So this is, I just start off with a few kind of famous images, very famous images, early days of visualization. So this is one about some in a military kind of setting. So it's a diagram of the causes of mortality in the Army in the East, right, from 1855. And what we see on this polar axis are months, right? So the months are rotating. So July, August, September, October, November, December, and so on. And every month has a wedge, like a pie chart. And then the size of the wedge indicates the number of deaths. So the bigger the wedge is, the radius, the more people died, or soldiers in this case, right? And what the person that generated this image was trying to convey is that deaths in the Army are preventable, right? And how are they doing that? So in the blue color represents preventable disease deaths, and then red represents deaths from wounds, and black represents death from all other causes. So you can see that like the black is non-preventable deaths, but the majority of deaths are in blue, so they're preventable, even though this is deaths occurring in the Army. And it also shows that the disease deaths are happening mostly in the winter. So it's a very good way to communicate military policy in this particular case, right? Don't go to war in the winter time, you know, if you want to prevent a lot of people from dying, or the majority of deaths, right? So it's a very effective way to communicate that kind of information. Or just don't go to war would be would be another solution. But never mind that. So that's a very famous image, by the way. You'll see that. That's not the last time you'll see that image. You'll see that image several times over the course of your lifespan. Yeah. So why do we use visualization? So the visualization exploits our visual perceptual system. So if you study the brain, most of our brain cells are dedicated to vision in the visual system. something like 30% or something like that of our perceptual brain is dedicated to vision. The second closest, I think, is audio, and that is something like 8% of our brain is dedicated to processing audio signals. And then touch is something like 5% or less. So the visual system is occupying a lot of our cognitive processing. It's way beyond all the other senses, like way beyond. So it makes sense to try to exploit that, right? So we can exploit that with visualization. So the human visual system is very powerful, right? So it's very good at forming groups. It's very good at identifying boundaries or borders. It's very good at identifying paths, patterns, and it's very good at comparisons. Like this is what our visual system does. And visualization, especially, we're going to focus on information visualization. It lets us perform different things with data, so we can explore data. Data exploration is when we're trying to understand a data set that we don't understand already. So we could be just trying to figure out what the data set is. We might not even know what it is. We're just trying to figure out, for example, how big it is, if there are any general patterns or trends, what the distribution looks like. So that's the case when we're unfamiliar. We can use visualization for analysis. So that's when we already are familiar with the data set. Maybe we collected it ourselves, or we know the people who collected it, and we want to confirm or refute a hypothesis, right? Or we want to answer a question. Visualization can also be used for communication, right? I just used it for communication just now in that previous slide, right? So whoever made that image was trying to communicate, hey, we can save a lot of lives if we just don't go to war in winter, for example. And another thing that visualization can do is verify and build confidence. So when you get more experience, you'll discover that data collection is usually done with kind of a process or a system. And a lot of times, those processes and systems that collect data have errors or systematic flaws. And visualization is very good at highlighting and pointing out systematic error and systematic flaws. That's usually the first thing that happens, actually, is you generate an image of a data set and you discover there are problems in there. That's usually the first thing that happens. So visualization is good at verifying and building confidence. Another point that I didn't list here is visualization is extremely good at searching. It is the best way to search, basically. You can find things in a second that are otherwise sometimes impossible to find through a manual search. So it's very, very good at searching. This is a little image of the so-called visualization pipeline, which we won't go into in detail. It starts with raw data, then it generates some transformation, like usually some processing, like putting the data into tables, and then mapping some visualization primitives to those tables, and then generating images, and then we have an observer. The observer usually interacts with the visualization or the images, right, to modify them. Here's another very famous image, Napoleon's March to Moscow. Has anybody seen this before? It's a good one, right? It's whatever you do, don't try to invade Moscow. So it shows the path from Paris to Moscow, right? So here we see Napoleon's army. The width of this path represents the number of soldiers in the army, right? And then the x-axis represents time. So as we go from right to left, the passage of time is occurring. So you can see that the army is dying or shrinking as it gets to Moscow. And then there's a return. And by the time the army returns, it's quite small, right? Almost everybody has died. There are some more variables in there. So we have the army size, we have time. There's also temperature being mapped here. So a lot of soldiers just died from cold temperatures. That's what that's indicating. Another variable we're encoding in this image is just location too, right? So Paris is southwest of Moscow. So that's not perfectly encoded here, but you can see there's a little bit of geospatial, a little bit of geospatial encoding here. And there are special notes too. They're written in French though. Anybody here know French? Nobody here knows French? Okay. I don't know. I studied French, but I don't know it. Anyways, this is a very famous image. It's one of the most famous images in the world, actually. Yeah.
Probably Hitler didn't have that image. Probably Hitler didn't have that image. So you can look at this one.
But you can see more details if you have a close look at it. One of the reasons it's famous is because it shows what happened to Napoleon's army so effectively. It shows like 5 variants very, very quickly and effectively. It's not very difficult. Question?
What do the branches look like?
Which branches?
Towards the beginning of the figure.
Like these?
Yeah.
I'm going to guess that these are kind of different paths. These aren't to Moscow, but just a different location. Yeah. If I could translate the French, then I probably would find out what those are. But that's a different path, right? There's some important location there that's not Moscow, but I don't know what it is. And I don't know if anybody studies history, but like clearly Hitler did not see this image, right? Because Hitler made the same mistake just a few years later. He should have taken this module. So we can encode data in something called visual variables. So one of the first ever visualization books was by a French scientist, Bertin, The Semiology of Graphics. And he identified what he called visual variables. So for example, position, we saw position on the previous image. Size, we saw size on the previous image. Brightness, we didn't really see anything about changes in brightness in the previous examples. Color, we saw color encoding. By the way, the color here, the orange, or whatever you want to call that, the beige is on the way to Moscow, right? And the black is on the way back to Paris. Orientation, we saw a little bit in the geospatial positioning. Texture, that image doesn't use texture. We can also use area. We saw area encodings in that image. Volume, we didn't. That's for 3D. Shape, we did see some encoding in the shape, right? Like you asked, there's a shape there for the different destinations. So we can use all of those things to encode data. That's all those visual variables, right? We can indicate the same data in many different ways, right? Here's some examples. We can indicate test scores with an area, a height, or brightness, right? And then the question is, which one of these is better? Anybody want to guess? How would we find out which of these is better? Anybody want to guess? If we wanted to answer that question.
Yeah, let's keep it.
That's right, that's right. You'd have a user study, right? And you'd ask people to say, okay, what do you think Ant's size is relative to Bert's size? Oh, I see Bert. There's a little arrow there. That's supposed to be Bert. Right, and you'd ask them these questions, and you'd ask maybe 50 different people, and then you'd measure their accuracy and their response time, yeah, to find out the answer. But in this case, from previous experience, we know a good choice is the bar chart here for this for those kinds of comparisons. We could take those visual variables and divide them into so-called marks and channels. This is this terminology I find confusing, by the way. I personally don't think in terms of exactly this terminology, but it's good for kind of teaching purposes, right? Marks can be, for example, points, lines, and areas. So we can encode data in points. We describe points as having zero dimensionality. That's what 0D means. We describe edges or lines or curves as one-dimensional, and that one dimension is length. And then areas we describe as two-dimensional, right, because they have a width and a height. Everybody's phones are like going crazy today. There must be something special happening. The building's on fire. I'm just kidding. And then we have so-called channels. So what can we do with the points, edges, curves, and areas to modify them to encode more data? That's what the so-called channels are. We can modify their position, right? Horizontal, vertical, or both. We can modify their color. We can modify their shape. We can modify their tilt, angle of tilt. We can modify their size. In a 1D instance, it's going to be length. In the 2D instance, it's going to be area. And then in a 3-dimensional instance, it's going to be volume. So we can use these marks and channels to encode data, right, as a visual representation of data in different ways. So channels can be used to indicate quantities, how much of something is shown in the data, right? We can use position, length, saturation. That's color saturation, by the way. So different. We can use channels to represent ordinal data, so something that's less than another thing, right? Small, medium, and large. Here, just the size is changing and the position. And we can use channels to represent quantitative data, data that is subject to mathematical operations. Right, 10 centimeters, something measured in centimeters, something measured in degrees, and so on. Right, there's tilt being used to change or represent data. This is color, right? Minimum value and maximum value being represented by color. We can use channels to identify what is where. So channels could be shape, color, also called hue, or position, or spatial positioning, right? Channels can also represent categorical data, so data that belongs in a category, not numerical data, right? Like apples, oranges, and bananas, that's a categorical data. right? Student data is usually categorical, like undergraduate, master's student, country specific, and so on. And this is just a little summary that tries to indicate our visual preferences. Like each mark and channel has a kind of strength and a rank. And there's different research to try to rank the strength of these marks and channels. Like if you have to choose between area and position, like what do you choose? Right? Which one is more effective at encoding data or representing data? So this is trying to rank those channels, right? So position is ranked very high, right? If you're trying to choose how to encode some data, position on a scale is ranked very high, very effective. On an underlined scale is also very effective. Length is very effective. Then tilt, then area, then depth, color luminance, color saturation, curvature, and volume. So that's a kind of ranking. If you had different options, you would probably start near the top and work your way down. And then for the identity channels for categorical data, you might use spatial position as your top most effective encoding, then color, then motion, which I think I have a slide for that, and shape. So spatial position is the top rank, then color is ranked second, and animation is ranked third, and shape is ranked fourth. So if you have a choice between how you're going to represent some data, you can start at the top and work your way down in terms of effectiveness. And this is too small to read, but there are lots of resources. So if you're trying to make decisions about how to represent data and what chart to use and when to use them, there are resources that you can use to look these things up. Right? There's a category here called derivation. So if you're trying to show or convey derivation, then you could use these charts. If you're trying to convey correlation to see if variables are correlated with one another, you could choose these charts, right? The first one is a scatter plot and so on. If you're trying to depict ranking, you can use these charts and so on. Distribution, change over time. Look, that's the biggest one. It has lots of different options there. If you're trying to compare magnitude, here are lots of different options and so on. Right? And there are lots of guidelines. There are lots of resources, visualization resources and guidelines. This is just one of them. And it shows cases of what combinations are good together, like shape and points or position is good when you want to show qualitative differences, right? Size and points are a good combination when you want to show quantitative differences. And then color is good for qualitative differences, right? And color value is good for showing quantitative differences. Qualitative, remember we used those terms quantitative and qualitative last week, hopefully. And then texture. So these are just examples of different marks and channels being used together and when they're a good combination, when they're a good choice to use. Our brain, has anybody read the book called Thinking Fast and Slow? Anybody read that book? it's quite an interesting book. If you have a chance to read it or listen to it, it's very, very popular. It's really popular, that book. And it's related to this slide. So our perceptual system has different rates at which it processes information. And there's a fast processing time and there's a slower processing time. And it's very similar to the way we think. So when we think, we also have a very fast gut reaction, like a knee-jerk reaction. When we see something or something happens, that's the fast part of the thinking. And then we have a slower, more careful judgment and thought process afterwards, right? It's the same thing with the visual system. We see some things very quickly before we even realize that we saw them. And like for example, 0.2 of a second. And then we have a slower part of the visual system that like processes our images consciously, right? So if we're processing something very fast, for example, in less than a half a second, we call that pre-attentive processing. So that's processing that happens in the subconscious very fast in less than a second, even less than a half of a second, that we're not even aware of, right, necessarily. So size can be processed pre-attentively in less than a second. So can orientation, color, curvature, motion, shape, and there are others. But those are all visual encodings and visual properties that we can see in less than a second. Like our perceptual system sees it very, very quickly. Here's an example of that. In which of these cases is it easier to spot all the threes? Right? If we look at the first image, it's difficult to see all of the threes because we have to look at every individual number to locate them. And even if we do that, there's a good chance we're going to miss one, right? But if the threes are highlighted in red, you can spot them in less than a second. You can answer that question in less than a second, right? And if we use area, it's also pre-attentive, but it's not as quick as the color, right? It's not as easy as the color. But if I did a test that said something like, okay, I'm going to show you a slide for 1/10 of a second. Tell me if there are any red numbers on there, and I just went like this, you'd be able to answer that question. Like you'd be able to spot the red numbers and answer the question like, yes, I saw red numbers, even if I show it for less than a second. So Gestalt theory is related to how we associate images and visual representations with one another. So when we perceive patterns or groups, right, we associate items with one another. So proximity is one of the ways in which we associate data with one another. So if it's located close together. Similarity is another thing we use for association, to perceive patterns in groups. Gesundheit. Closure, Gesundheit, is another property we use for groups, detecting groups or looking for patterns. Symmetry is another property our vision system uses. Motion, so there's an example of motion, right? We magically see this dog, even though there is no dog there, right? It's just a set of points. But our brain is putting together the motion, integrating that motion and saying, hey, there's a dog there, right? Continuity is another way we look for patterns in groups. and so on. Of course, we're affected by our past experiences and patterns that are regular, simple, and orderly, right? And so on. I'm going quite fast here, by the way. You know, those, like we did last week, we looked at kind of statistics, and we all know that we can take a whole module in statistics. So it's just like a quick introduction. It's the same thing today. You can take a whole module on visualization. Is anybody taking the Viz module? There's a visualization module. I thought it was open to master students. You are taking it, yeah. So you've seen all this stuff. You're gonna give the next lecture. So we're going through the visualization introduction kind of fast, but you can take a whole module on visualization, right? So we're just sort of scratching the surface and giving the introduction. And of course, we have lots of different kinds of data. I think everybody here knows that already. Categorical data, so data that fits into different categories. Numerical data, data expressed with numbers. Multivariate data. So, for example, things like temperature and pressure together, right? When you look at the weather forecast, it's multivariate data, right? You have a temperature, you have a humidity, you have a probability of rain, you have a wind measurement, right? That's multivariate data. Geographical data, right? That's data that's associated with a map or geospace, like we saw with the Minard's depiction of Napoleon's march to Moscow. Temporal data, right? Data associated with time or that changes over time. And then we have relational data. So data that compares things, right, with respect to something else. Right? Something might be a child or a parent of something else, greater than or less than something else, or somehow connected. And we use different visual representations for all these different cases. Actually, for all these different types of data. So, categorical data describes groups. I think everybody's very familiar with that, right? So we won't spend lots of time on it. Categories may have values, the amount of data in each associated with them, right? A person's grade on an exam, right? Our exam scores are categorized, right, into distinction, 2.1, 2.2, and all that different stuff. We have interval data, right, divided into categories. That's all age groups, categorical data. And categorical data is often put in these very familiar encodings like bar charts and pie charts, right? These are great representations for categorical data. And everybody here has made pie charts and bar charts before. Right? Has anybody ever like not made a bar chart or a pie chart before? Here's an example of a time-oriented image, right? We have time on the x-axis and then value of the stock on the y-axis, right? That's a time-oriented. That's also called time series data. So data that has a special time interval that's changing every day or on a periodic basis. We could use something called scatter plots for numerical and categorical data. Remember, this was one of those charts found in the correlation category. So if we're trying to understand the relationship between two or more variates, We can use something called scatter plots. These are some examples of scatter plots. These are kind of special scatter plots though, because they're using glyphs. Here's an overplotted scatter plot, and here's the same scatter plot, but now grouping the data items into hierarchical glyphs. We can have multivariate data, right? Data that combines several variates together, right? Like age, gender, height could be all combined in one visual representation. There are some dedicated multivariate images and visualization techniques like multiple bars and bar charts, radar charts and parallel coordinates. Sometimes charts are combined together. This is actually also an example of a multivariate visual representation, because these are glyphs and they represent multiple variables. And the variables are encoded in this glyph legend, right? The position of each glyph encodes something, right? The average number of calls in a day. And then the y-axis encodes another variable called Net Promoter Score, right? And then the colors encode, well, I should say each glyph represents a group of agents in a call center. That's another variant, right? And then the color represents the department they work in. So there are lots of variables here being represented at the same time. That's a multivariate data example with a multivariate visualization technique being applied. This is a question that everybody is obsessed with, right? Which sport is the toughest? Who's the toughest? Rugby or American football, right? That's everybody's like obsession. This is a radar chart that tries to make a comparison of the different sports, like which sport is the toughest. And how does it do that? It looks at all these different aspects of a sport, all the different dimensions, like the strength required, the speed required for the sport, the power required, the so-called nerve, hand-eye coordination, flexibility, endurance, durability, analytical aptitude, agility. So it tries to measure these different dimensions or variants of a sport and then plot them on a radar chart. I mean, this radar chart is tough to read, right, because of all the overlap. But anybody want to guess what the toughest sport is? Here it says boxing. Boxing is the most difficult. I have to intuitively say that's probably a good guess. Like, definitely don't want to do boxing. And then the lowest ranking is fishing. I didn't even know fishing was a sport. Another common multivariate visualization technique. Has anybody seen parallel coordinates before? The people doing InfoBiz? Do you guys see that? The parallel coordinates? No, you haven't seen that yet? It doesn't look familiar. Okay. Okay, well, you're going to see it. So in this case, every variate is mapped to an axis. So this is a representation of a set of cars, right? And we're shopping for new cars. We want to make comparisons between the cars to see which one we want to buy. In this case, every car is mapped to a polyline, one of these lines that traverses the axes. And then the axes represent different attributes of the cars, like how many cylinders the car has. Maybe it has 8 cylinders, 6, 4, 2, or 1. That's very surprising. Okay, no, this is not 1. That's 3. And this is the displacement, the so-called displacement in cubic inches. So they related to the engine volume of the engine. And then we have the weight of the car, each car. We have the horsepower of each car, how quickly it accelerates from 0 to 60 miles per hour, how much fuel it uses, like the consumption, and then the year in which it's manufactured. So probably we would be looking for some car that has good fuel efficiency, right? So the high fuel efficiency is up here, and then the low fuel efficiency, or the better fuel efficiency is down here. Right? Oh, sorry, it's the other way around. Here it's 9 miles per gallon, which is very inefficient, right? Very bad car choice. And up here we have 47 miles per gallon. So if this was interactive, I would select this polyline, and then it would highlight which car it is, and I would choose that car to buy, right? Probably something like that. I know I'm going very quickly here. And we saw some examples of geospatial visualization already. Data that's represented usually on a map, right? Population health is often represented on a map. Meteorology is often represented on a map. Political data is often represented on a map, right? And there are lots of geospatial tools. Everybody here uses Gesundheit, Google Maps. Everybody here uses Google Maps, right? Where are the items of interest located? Where are the most frequent occurrences of a variable? Are there any change in populations of interest? So that's usually people-centered data, right? When you're studying populations, usually that's associated with geospatial visualization. Here's our favorite example, homicides in Washington, D.C. Right, we can show this on a map where, you know, there are these glyphs, right, where there are homicides, and those are the locations of the homicides, and then how the homicides occur with guns, with knives, or with other kinds of weapons, or whatever you want to call them, right? And there's some density indicator. So it looks like this street, you don't want to live on that street. Right. Has anybody ever looked at this kind of data before, crime data? That data is usually publicly accessible. So you can look up crime data in Nottingham. You can go to the Gov website, look up the crime data, and look at the locations of all the different crimes and stuff. Same with the US. I think a lot of countries, most European countries, you can look up that data. I don't know about Asian countries and so on, but in the West, you can look up this is all publicly available data. Here's another, this one combines geospatial and multivariate techniques together. Does anybody know what this is a map of? Anybody know what that is a map of? Nobody recognizes that shape? UK, correct. Yes, that's right. It's leaving out Scotland, though. So England, that's what England looks like. And then it's divided into regions. Those regions, anybody know what those regions are? That's a very difficult question. You'd have to be very smart to answer that. Those are called CCGs, clinical commissioning groups. That's how the NHS is divided, right, into clinical commissioning groups. And then each glyph represents a clinical commissioning group or a region, but it's showing the population health, right? The different dimensions of population health mapped to a pie glyph, right? So we have like the big blue is mental health, right? The prevalence of mental health conditions. Then we have stroke and heart disease. We have cancer, epilepsy, learning conditions, and so on. So you can see the prevalence of these different conditions depending on the regions. And so, for example, one thing you can notice immediately in just 1 second is that mental health is a very prevalent health challenge in all the regions. But then you can also see, like, okay, down here in the Cornwall area, it's not as prevalent as in London, for example. So you can see those sorts of things very, very quickly, right, with visualization. I think everybody knows and everybody's familiar with temporal data, data that changes over time. So I won't have time, no pun intended, to cover every slide today. I'll just skim through the last few, so that's a time-dependent plot. We have hierarchical data that can be represented with trees and tree maps. Anybody seen this before? Definitely want to see that if you haven't seen that. So getting an image of the market in just a second. That's a tree map. It's for hierarchical data. We have graphs and networks. Right, connectedpapers.com is an example of a graph or a network showing the relationships between papers, right? Which papers cite other papers. We have interactive visualization, so that lets the user change the parameters of what we're seeing, right? Selection, filtering, and those zooming, and those sorts of operations, right? So if you want to see everything in more detail, I do have a visualization course online. It's called Data Visualization Classes 2019, and it goes into all of these topics. It's the full course on data visualization, right? And we have a very, very helpful resource called Visualization Resources, a survey. And it covers like all the different visualization resources you'd ever want to know about. Where to find the visualization literature, what are the best visualization websites, what are the best visualization tools, what are the best software packages, blogs, YouTube channels, like everything. Okay. That was my introduction to visualization. Any questions? We will stop here. You're free to go if you're happy. If you're happy, you can go.